or so of these pieces. And these pieces are called tectonic plates, or just plates for short. Tectonic is a reference to the fact that they move. They move. Now, over time, plates will change shape, change size, change the direction of motion, and change the rate at which they're moving. And of course, they are moving, so they are also changing their position, their location. If you have your book, you can go to page 111. Page 111. It's a map of the Earth and its major plates, along with arrows to represent the approximate direction of motion and the approximate rate at which it's moving. Now, according to the caption, that's been determined by GPS, the Global Positioning Satellite System. So we can measure, with today's technology, we can actually measure in real time the motion of these tectonic plates, and we know they're moving. North America, which is this big kind of tan continent here or over here, and it's moving roughly west, moving approximately west-southwest, moving that way. We're moving that way. At just about an average of almost 5 centimeters a year. That's almost 2 inches a year. Can you feel it? Slowly moving that way. So even when you're standing still, you're moving. Kind of creepy when you think about it. Now, what's causing these plates to move? Well, we have heat rising up from deeper within the Earth. And this heat is driving a lot of convection, a lot of circulation, and that's in part helping to push and pull the plates around on top of that asthenosphere. But we also know from seafloor spreading that we have the motion of the continents from the motion of the ocean floors. Many continents, most continents, have a bit of oceanic crust attached to them. Here's our ridge. The ridge is always going to be elevated. It's going to be higher because there's heat there. There's heat rising from the Earth's deeper interior. That's hot. That heat producing magma or molten rock, and that's building underwater volcanoes. And it's those volcanoes that make up the mountainous region of the ridge. The center of the Atlantic Ocean, there is a ridge. The water above that ridge is only about 4 miles deep. You go just a little bit west or a little bit east of that ridge, And you're suddenly in water that's well over almost 6 miles deep. The ridge is higher. There are mountains under there. Some cases a few thousand feet tall. And it's also elevated because of the heat. Heat makes things rise, makes them lift. That's a high spot. At the other end, you can have a trench. A trench is where that oceanic crust is diving back down into the mantle underneath the continent. That process is called subduction. Sub means under, means beneath. Shun is coming from the Latin ficare, means to make, action, action. So we're basically putting something underneath. We are subduing the oceanic crust. It's like you'd subdue an enemy, put them underfoot, conquer them. That oceanic crust is being subdued underneath the continent. It's being forced back into the mantle. What's going to happen to that as it goes deeper and deeper into the mantle, where it's hot? What's going to happen to this? It's going to melt. Where's all that melted stuff going to go? Up. And it'll form volcanoes on land. This is a volcanic arc. We have a volcanic arc from subduction in our own country. It's in the Pacific Northwest, from northern California through the states of Oregon and Washington and into southwestern Canada. That is the Cascade Range, which includes Mount St. Helens, Mount Rainier, Mount Shasta, Mount Hood, Lassen Peak. They are active volcanoes. They can pop at any time. And they're being fed from magma, from molten rock, coming from the subduction process offshore. There's a small little plate. It's on, if it's on here or not. Yeah, it's on here. It's a tiny, tiny little thing. It's called the Juan de Fuca. I can't make this stuff up. It's the Juan de Fuca. It's a tiny little oceanic plate that's being subducted under the Pacific West coast. So you get volcanic arcs. If these volcanoes are out in the middle of the water, then there'll be a volcanic island arc, like we have in the Caribbean. All those little cruise ship islands, your St. Lucia, St. Martin, St. Vincent, all those little, they're all little volcanic islands. The Atlantic, there's a portion of the Atlantic Ocean that's subducting there. No, that's not right, I'm sorry. It's, what do you call it? The Caribbean plate is subducting underneath the Atlantic Ocean, and you're getting volcanoes. You also have to remember that these plates are made of rock. They're not smooth. See, they might look all nice and smooth and even in a line drawing, but they're not. They're rock, they're rough, they're jagged, they're pokey. So when the subduction process occurs, it's not just a whip into the mantle it goes. That subducting plate will periodically become hooked and snagged and hung up on that continent as it tries to go back into the mantle. So there are times when that will get hung up, and then it will break free, and then it will snag, and then it will break loose, and then it will catch on something, and then it will break loose. Every time it breaks loose, we feel that energy on the surface as an earthquake. So these subduction areas can also produce very powerful earthquakes. Here is the trench, and that's going back into the mantle. Some of these trenches can be several miles deep. It's very, very low in elevation here. And that's because this crust is very cold. It's too far away from the heat source to stay elevated, to stay warm enough to be lifted. So the farther away that ocean crust gets from that heat source, it's going to get colder. And as it gets colder, it's going to get more dense. And it's going to sink deeper into the underlying asthenosphere. And it'll get lower and lower and lower. So what's forming here is a slope. You have a high spot here, and a low spot here. That's a slope. What other things have a slope? Slide, a ski jump, suicide hill. Call it that for a reason. What do we do with those kinds of slopes? What do? We use them for what? Slide, right? To go from the top to the bottom in a hurry. That's gravity. Gravity is always pulling objects that are elevated down to areas that are low. So what happens here is that with this end being high and this end being low, that oceanic crust being so dense and heavy is going to slide always towards the low end. So it's going to slide this way and that way. That process is called ridge push. And it is what is pushing apart those plates at the ridge. As long as they continue to be pushed apart, that allows more heat to come up in the middle, and it self-perpetuates the whole process. Every time that rising hot material comes to the surface, it cools and hardens, becomes brand new rock. And some of it's pushed to one side, and some of it's pushed to the other side. Now on this continent, this oceanic crust is attached to the continent. So if this oceanic crust is being pushed by ridge push this way, it's going to push the continent that way as well. That continent's going to move this way. Any questions? Okay. Don't you wish your notebook were this big? Ocean. There's another continent. Well, we can also have this scenario, where that piece of oceanic crust that's attached to the continent is entering subduction. Now what's going to happen here is another process called slab pull. And that's also going to help move the continents around and help maintain the seafloor spreading process. As this oceanic crust descends into the mantle, it's not a two-directional object like what you see drawn here. That plate is a three-dimensional piece of substantially large rock. This whole thing is subducting into the mantle. It's just, I'll do it this way. This whole thing's going down like that. That's heavy. Oceanic crust is thin but dense. It's not going to take long before gravity is going to grab that and just pull it in. It's like my book. I can push it over the edge, and there'll be a point where I don't need to push it anymore. Gravity will pull it the rest of the way over. Friction. There it goes. That's slab pull. So basically what's happening here is that once this subduction gets started, gravity is going to take over and just Reel it in. What's at the other end? Another continent. Continent, thick but light and fluffy. So yeah, it's so connected. It's not just like, okay, we're going over here. Okay. It goes wherever the crust takes it. Doesn't really have a lot of choice. So as slab pull is pulling this in, that continent over there is getting closer and closer and closer. Now eventually, all of this ocean crust will go down into the mantle. And these two continents will slam into each other. Continental crust is light and fluffy. It's not going to want to sink into the mantle. It's going to want to float. It's going to want to sit high on top of it. So you're not going to subduct continental crust. So if down isn't an option, what's left? Up. So when these two continents collide with each other, they will lift very tall mountains. This is how we get the Himalaya mountains that are currently continuing to form between India and Asia. This is how we got the Appalachian Mountains to our east. We were smacked first with Europe, and then we got slammed by Africa. That caused some damage. I didn't even know. Sort of bam. So, now again, unfortunately, it's not something that occurs over like a weekend, where you could go and watch it. That'd be like really awesome, but we'd probably kill it. It's something that's going to occur over the course of several hundreds of thousands of years to several millions of years. So you definitely get the formation of mountains. Yeah, pretty much. Pushing and pulling it around. Yeah. Alfred had, Alfred Weiger has lived long enough to have access to technology that Harry Hess did. He would have had this figured out a long time ago. But seed force spreading is the key point that he was missing. Because he could not explain, he could not envision how those continents were moving about. But seed force spreading answers that. Are there any questions?
Do they have any idea how long that would take to happen?
For what happened?
Or with an inclusive continent?
Well, we're moving south-southwest about 2 inches a year. At that rate, we'll probably hit Australia in about 10 million years. So not much. Well, unfortunately, no. It's not that Yeah. It'll be long after the sun's gone supernova. There's nothing here anyway. Yes?
So basically, like, moving it for another time.
Yeah. Well, because the plates are moving, the Earth is round. So if they're separating on one side, they're going to come together eventually somewhere else. Current models, because we play with that, we model things and try to project things into the future. Current models actually show subduction occurring in the Atlantic and bringing us in Europe back together again. That'd be nice. The air carriers would be cheaper, but it's not going to be. Question?
The difference between the ridge push and the slab pull is the subduction on the slab pull has got a sharper angle, right? And this is a longer, gentle.
No, doesn't matter. No.
So what causes one of the versus the other?
Yeah. In ridge push, the ridge is higher, literally higher in position, and the trench is lower, and that gives you a slope. And so it's so heavy that once you angle it, it's just going to slurp from one end because of the weight. So that's ridge push. It's pushing to either side of the, it's falling away.
Yeah, I understand the concept.
Because it's sliding down. And in slab pull, once that subduction gets started, again, it's so heavy that once that starts, it just gets pulled in by gravity, and that keeps it moving. And see, then again, on the other side of this continent, and you get the other coastline from this thing, and it may be another ridge. You have another ridge over here. So you have ridge push on this side, pushing it that way, and subduction on the other end, pulling it that way. So it's all connected one to the other. Here on North America, we have a ridge to the east. Our North American plate actually begins in the middle of the Atlantic Ocean at the Mid-Atlantic Ridge. That ocean is attached to our east coast like a leash. It's connected to us. And then our continent extends all the way to the west coast. And then along the west coast, we have a combination of subduction processes and sliding processes. Any questions? You got to figure the Earth's round, and it can't get bigger or smaller. It's just got to, recycle the shape and size it already has. So if you're going to spread things apart at one end, they got to come together on the other. Yes. Yeah. Well, we surely won't be here in 10 million years. We'll be long gone. And then, I don't expect to be. I mean, it'd be cool if I could be, but I don't expect to be here in 10 million years.
Right. Will the land still be able?
Plate tectonics will continue to operate as long as there's still heat coming out of the Earth's interior. So as long as the Earth's interior is still hot and there's sufficient heat coming to the surface to help power this, then yes. And by some estimates, the Earth's got at least another 3 to 5 billion years of heat left. So, it's going to take a while. It's hot down there. It takes a while to cool that off. Does that answer your question? As an example, the collision of India into Asia began the formation of the Himalayas. Here are the Himalaya mountains here. We're number one in India there. That process started about 80 million years ago, and it's continuing today. India is still pushing northward. These mountains are rising at an estimated ½ inch a year, but unfortunately they're also being worn down at about the same rate. So they're pretty much staying where they're at. Questions?
I know it's kind of weird, or a different question, but how much of these theories have been compared to other planets?
All of them.
I mean,
Yeah, there's some evidence of plate tectonic activity having, at one point in time, operated on Mars, but Mars' core is cold. It's solid, so that process is not happening anymore. There are also suggestions of plate tectonic-like activity on some of the moons of Saturn and Jupiter that don't necessarily involve like hot mantle so much as it's currents of like frozen methane and changes in gas pressure and things like that. But the general mechanisms appear to be roughly the same. Yeah. So, definitely. Now, whether or not this holds true everywhere.
the theories of it.
Yeah, I mean, it's working for now, but if we end up on some planet somewhere and things are different, we'll have to come up with something different for that planet or amend this. Does that answer your question?
I just am more curious along the lines of, I know they do that, but how much do they still?
Oh,
abandon it? Or
no. NASA and other space agencies do employ astrogeologists, which are Earth. They're star Earth studiers. Astro. They study the Earth as it applies to other planets. Any other questions? I heard a good joke yesterday. You want to hear it? Are there any Ohio State Buckeye fans in here? Go Bucks?
Go Bucks.
All right. How do you get a Michigan graduate off of your porch? You pay for the pizza. Implying that a Michigan graduate is delivering.
I didn't get it.
I didn't either. Took me a second.
It's early. And if there are Michigan fans in here, well, let's just do that. I mean, we don't call ourselves the Ohio State. Okay. So we have these big plates, and they're moving, and as they're moving, they're going to be slamming into each other, bumping into each other, touching each other. Most activity is going to occur where plates interact, along their edges. We call those plate boundaries or plate margins. And there are three ways that these plates can interact. We got two of them still on the board. Don't see the matters to me. Oh, okay. Divergent, convergent, and transformed. Divergent, di, means to separate, means to split, like in division. So divergent means that plates are moving apart, they're separating. That is a tension force, a pulling apart force, a pulling, stretching, thinning force. Tension. C-force. C-force spreading, where ridge push is occurring, that is a divergent boundary. Plates are separating. As plates separate, it allows for hot material to come up from below. You're going to get volcanism. That molten material is on a hurry to get to the surface so it can cool off. So as that rises, it can also jostle and shove rocks out of the way. So you'll also get earthquakes associated with this volcanic activity. Hang in there. One more day, maybe a 3-day weekend. Hang in there. Now, convergent. This one gets a little tricky. The prefix you're looking at here is actually co, C-O, meaning with or together, like cooperate or coordinate. But convergent is kind of, a tongue twister. It's difficult to say. It's not fluid. So the N is to help it sound better. Convergent. Easier for you to say. So in this case, we're looking at co, meaning with, not con, meaning against. It's different. Just kind of ignore the N. So convergent means the plates are working together. They're coming together. They're moving towards each other. That's a squeezing or a compression force. It's going to give us subduction. Subduction is going to give us volcanism, earthquakes, And it's going to give us continental collision. Which is going to give us mountains. Any questions? So let's see. We have pulling apart. We have coming together. What type of motion left? Well,
Together?
upward and downward. Plates move mostly
Together?
laterally, side to side, so up and down.
Together? Both going the same direction?
Same direction? No. So you guys are a lot more creative with that than my other class was. What? Sliding past each other, one going one way, one going the other, like two cars trying to get down the same alley going in opposite directions. Yeah? Yeah. That should transform. That's a sliding force. We call that shear. That's why they call scissors shears, because they cut from the blade sliding past each other. That's a transform boundary. We have a prominent transform boundary in our own country. We more lovingly refer to it as the San Andreas. I am having trouble with E's today. E. Through Southern California, all the way down to the Baja of Mexico, we have a transform boundary where the Pacific Ocean plate meets up with the North American plate, the one you're sitting on. North America is trying to move roughly west to southwest. The Pacific plate's trying to move roughly northwest. So they're going to collide with each other and try to slide past each other. These are made of rock. They're not smooth. They're all bumpy and pokey outy and tucky inny. So when they try to pass each other, they're occasionally going to get caught and snagged on each other. So they'll get caught, and then they'll break loose, and then they'll snag, and then they'll break loose, and they'll get caught again, and then they'll break loose. Every time they break loose, we feel that, well, Californians feel that, as an earthquake. So transform boundaries can produce quite powerful earthquakes. August 30th, 1999, northern Turkey. That's a transform plate boundary. They had a massive earthquake, killed an estimated 17,000 people. That's an estimate because the Turkish government did not have accurate census data. So there could very well have been close to 20,000 people. To this day, there are still people that are suffering the impact of that quake. They haven't been able to recover their jobs or their homes or their livelihood. Many of them have had to leave the country. They don't have the coverage of insurance available to them that we do in this country. For years after the quake, the suicide rate skyrocketed because people didn't have a job. They couldn't get out of living in a tent city. They had no money. They had no home. They lost everything. And they suffered from terrible depression. The Turkish government discovered after the quake that many people were killed because buildings had not been constructed to proper earthquake code, as was mandated. And further investigation turned up that several city and local inspectors and contractors had accepted bribes to cut corners during construction. And as a consequence, more than a dozen of these contractors and city officials went to trial, and the Turkish government executed 9 of them for their play in killing all those people. Yeah, Turkish people don't mess around, man. Guilty. Oh. Next. That's it. Yeah. An eye for an eye, or a head for 10,000 people. So they can form really powerful quakes. You're not going to get mountains at transform values. Because why do we call something a mountain? When you're looking at a mountain, what does your head do? What's up? You need up for mountain. We don't have up doing this. There's no up in this motion. So you don't get mountains from this. You're not going to get volcanism because volcanism needs magma, needs melted rock. Now you can have friction to generate quite a lot of heat, but no matter how hard you do this, your hands are going to go, no. Okay, right? At least I hope not. Right? Unless you have like magnesium or something in there, and I would recommend that. So even at a transform boundary at that scale, there's not enough friction there to cause enough melting to produce the molten rock you need for volcanoes to form. So you can forget the movie Volcano. You've seen that one, it's a stinker. Where they had the volcano coming out of the La Brea tar pits. No, that was a while. That was ages ago. That was decades ago. I'm sure it's on Netflix. If you want a really bad movie, you look that one up. It's bad. It's so bad. The prominent geologist was, I can't remember her name, who played that part. She was a chick. And they just made her look so stupid. It's so hot. I remember one scene, she's in like a cotton shirt and shorts, and we're down in the subway, and she's about from here to that globe from a mound of magma, trying to take a temperature reading. And she said, oh, it's 700 degrees. I'm like, okay, the flash point for cotton is about 475. This is standing torch right now. People, scientists are in Hawaii in asbestos suits, I had to take a sample, it's really not, it's not working. Yeah, Hollywood. So no, transform boundaries, you're not going to get volcanism. This is not, you don't generate enough heat to make the molten rock. Are there any questions?
So if you want to become a scientist, you should go to Hollywood.
Oh gosh, don't go to Hollywood, don't see any movies. We were complaining about that again this past week. The core, I don't know if you guys remember that movie, The Core. And there's something wrong with the Earth's magnetic field, they could go down to the core and recirculate the outer core or something stupid. And it's impacting the magnetic field, it's all screwy. So it's like all of these birds are like flying into windows and buildings and things because they navigate using the magnetic field. Yeah, but they're not blind! They only use the magnetic field to migrate. They use their eyes for everything else. It's kind of like, what? Oh, and this isn't enough. We can also get activity within a plate that's far removed from any of the edges. And this is known as hotspot activity. Hotspots are still poorly understood in geology. Still trying to work on really trying to figure this one out. We know they exist. We know that some of them have capacity to last for tens of millions of years, if not longer. We don't know really what gets them started in the first place. We don't really know why they are, where they are, and we're not really sure just how long they last. We don't know completely, we don't know what the mechanism that keeps them going. But we do know that they are very concentrated, very localized, kind of like a spot, where you have just jets or plumes, columns of very hot mantle material rising to the surface. So it's very hot. That's the term hot spot. In your book, trying to find out what page those are on. I know it's in there. Is that on page 100? 101, yes, thank you. Page 101 show all of the Earth's major hotspots, and the red lines show where it's been, and the dot is where it is today. We have two hot spots in our country. One is in almost the dead center of the Pacific Ocean, and that's the state of Hawaii. Hawaii is a hot spot. As that hot material rises from below, it melts through the crust and produces volcanoes. Those volcanoes continue to build until they're high enough to make an island. The Hawaiian Islands are among the tallest mountains in the world. They're even taller than Everest. Because if you measure them from the sea floor, they're over 7 miles high. Because they're coming up through a good 6 miles, 5-6 miles of water first, and then from the water line up. Right now, there is a new island forming just south of Hawaii, and it's forming because as that Pacific Plate moves, it moves those islands away from that heat source, and it's going to start all over again, forming a new island. These spots don't appear to move. It's the plate that's moving across the top of them. It's like moving a sheet of paper over a lit candle. Every now and then it melts through, and poof, you get an island. This new island is estimated to be another 15,000 years before it's above the waterline. And they've already named it. It's called Hawaii. And they're probably going to be taking hotel reservations in the next decade or so. Got to plan ahead. But Hawaii will be the next new Hawaiian island. Back in the mid-90s, there was a new island over near Tonga. That's way over here, Tonga. So a little satellite, like one of those survivor islands over here in the Pacific. And it was also from a hotspot-related activity. And it broke the surface as an island in the mid-90s. I don't remember. They probably have a name for it now, but I don't remember what it is. We have another hotspot in our country. It's located in Wyoming. That's known as Yellowstone National Park. Yellowstone National Park is also known as a supervolcanic area. It has a geologic history of very violent, cataclysmic volcanic eruptions because of that hotspot. Beginning in the 1980s, scientists detected magma within 2 miles of the Earth's surface, rising to fill the underground magma chambers below Yellowstone. Since then, there have been changes in earthquake activity, changes in geyser behavior, and changes in land elevation. As that magma rises and fills that chamber, the land swells. So there's the potential for eruption. The hope, among many, is that the eruption cycle occurs in stages, which it has in the past, rather than all at once, which it has also done in the past. It's under constant 24/7 monitoring. The hope is that it can give us some heads up, and that we may have as much as 72 hours to evacuate 9 states. Ohio's looking pretty good. Yeah, they've been looking at trying to evacuate Montana, the Dakotas, Colorado, Wyoming, Nebraska, and Kansas. And they're going to be telling them to book east towards us. Now, if you think of when there's a big hurricane coming into Florida, and you see it's on TV like a week before it makes landfall, and the guys on the Weather Channel are telling people in Florida, get out, leave, and there are always people that don't leave, or that try to leave at the last minute. Can you imagine trying to evacuate 9 states in 3 days? They're not going to leave. They're not going to believe that it's going to erupt. That was the problem with Mount St. Helens. 60-some people died because they didn't leave. They didn't believe the scientists that the volcano was going to erupt. I mean, we do occasionally err on the side of caution and tell you something's going to happen and then it doesn't, but that's just a freebie, okay? You just kind of have to assume we're right all the time and go for it. Yeah, there you go, yeah. It's kind of like the umbrella thing, you know what I mean? It's better to have it and not need it than need it and not have it. It's better to think the scientists are right and do what you're told and save your life than it is to risk it and stay behind and, oh, snap.
Oh, hey, look, lava.
Lava, yeah. Any other questions?
Good luck taking pictures of that.
Good luck taking pictures. Yeah. What was that? Oh, stupid movie, 2012, was it?
Yeah.
I think it started. Oh yeah, the downside here is over here because the plates move. In a weekend? No. That's not physics. That's violates the laws of physics. It's not physically possible. The only cool thing is if you remember Kevin Costner in Waterworld, where they had the little girl with the map on her back, they're trying to find the land, right? Now apparently the whole Earth is underwater because of some massive nuclear war. What they do? Bomb all the mountain ranges? I don't understand how that's all underwater. But remember, and the old man figured out that no one could find the land because the poles had reversed, and so they were reading her map backwards. Remember that? You have Netflix it now. Look it up. That's like the only scientifically. I remember the movie theater. Oh! And that was those.
More ice caps and
Melted or something that happened.
Major war.
Yeah. But the problem with that is that even if all the ice melts today, sea level's only going to come up about 300 feet max. And, we're 720 feet here. So we still won't have the coastline. It'll still be 3 hours drive to the beach for us.
But I mean, maybe do that on the weekend.
Yeah, that's right. I digress. So hotspot activity. Definitely you're going to get volcanism because of the word hot. So definitely will produce volcanic activity. And again, that material, that molten rock is on its way, it's on a rush to the surface. So it's going to push rocks out of its way. So you're going to get some jostling and breaking of rocks, and that can also trigger earthquakes. Now, plate tectonic theory is considered a unifying theory in geology. It helps explain most of the Earth's internal and external processes. It explains the occurrence of mountain ranges, volcanoes, earthquakes. It explains a lot of the interior processes of rising heat and heat circulation in the mantle. Here's some of the harebrained ideas we had to try to explain mountain building and volcanism before we had plate tectonics. Now, looking back, it's so obvious. We wonder how they laughed at Alfred. But, they say about hindsight. Again, if Alfred had lived another decade, he would have nailed it. So because it's such a unifying theory, we'll be coming back to it over and over and over again throughout the term. When we talk about volcanoes, we're going to be talking about plate tectonics. When we talk about earthquakes, we're going to be talking about plate tectonics. When we talk about metamorphic processes and igneous processes, we're going to have to bring up plate tectonics. When we're looking at structural geology and the formation of mountains, we're going to be bringing up plate tectonics. When we look at glacier development, ice ages, climate change, we're going to be talking about plate tectonics. Any questions? So the Earth's lithosphere is moving. Top of that lithosphere is the crust. Crust is what we know the most about because it's what we have the most direct access to. So let's narrow our focus even more. We've gone from the Earth's interior to the lithosphere to the crust, and now we're going to take a look at what the crust is made of. The Earth's crust is made of rock. Rocks are made of minerals. Minerals are made of elements. There are a little more than 90 naturally occurring elements. And there is a table of them in the back of your book. It's called the periodic table of the elements. I've been running a series on PBS about how the periodic table was developed. If you have high school chemistry, this should look painfully familiar. I don't know about you, but when I was in high school chem, you had to know this chart. Hydrogen, helium, lithium, beryllium. I remember the names of most of them, but I don't think I remember what order they're in. About 90 of those or so are naturally occurring. They combine in different ways to form compounds, and these compounds are called minerals. Now, you may be familiar with the word mineral as in, you got to have your vitamins and minerals. Well, minerals make up those vitamins. If you're going to have an iron supplement, did you take your zinc today? That comes from a mineral. That stuff's mined and crushed up and put into your centrum. It's coming from the mineral. Your zinc, your iron, your calcium, magnesium, all the other stuff that your body needs to function properly. That's where that's coming from. Minerals, by definition, must occur in nature. They must be formed by natural processes. Cubic zirconia, man-made. Can't call it a mineral. You just can't. If you go to the jewelry store, the jeweler has to tell you if the emeralds in that emerald tennis bracelet are natural or if they're synthetic. Synthetic means they've been grown in the laboratory. They're man-made. Now they have all the exact same chemical and physical properties as the natural emeralds. They just look prettier. Why would you want to make our own emeralds? Well, we make our own emeralds, our own rubies, our own sapphires. We make a lot of our own minerals because in the laboratory, we can grow them faster. We can control their purity. We can control their optical properties and form absolutely perfect crystals that are very, very rare in nature. And if anything has the word rare on it, what else does that imply? It's expensive, yeah. And we use those crystals in a lot of optics for high-tech, like microscope equipment, detection equipment, and also the medical industry and research industry is lasers. So you have to make those materials synthetically, or you won't have enough of them in time. You can cook up an emerald in a week, and it has to be perfect crystal. You go through 4 tons of the real stuff trying to find the perfectness that you need. So they have to form from natural processes. Man-made doesn't count. They are crystalline solids. Crystalline. What that means is that the atoms that the mineral is made of have to be put together in a specific pattern. The atoms have to be put together in a specific repeating pattern. That's what forms a crystal. What shape that pattern is determines many times what the mineral is. I have 2 models here, made with these little round wooden black balls. They are both carbon, made of the element carbon. In this one, the carbon atoms are all arranged in these sheets, these parallel sheets, stacked one on top of the other. This is the mineral graphite, which is in your pencil. It has a hardness less than 1. It is among the softest naturally occurring minerals on this planet. In this hand, the carbon atoms are arranged in a very tight kind of jungle gym or scaffolding kind of pattern. Different patterns of how the atoms are assembled means that this mineral is diamond. It has a hardness of 10. It is the hardest natural substance. So you have the softest and the hardest substances in nature, both made of the same element, just in different structures. Yeah.
Is there usually wood from packs like that? That usually means I'm ordering.
It depends on the elements that it's made of. Carbon, what makes it so hard is that what's happening with this one is that all of the carbons are hanging out together, they're all connected to each other. So the bonds are the bonds holding the atoms together are very, very strong. So that makes it very resistant to being torn apart. But this thing, there's nothing holding the sheets together except those weak, like positive and negative force, so they split very easily. Just slide around. That's why graphite is used as an industrial lubricant, because it's so slippery. And it can withstand high temperature. So it has to be crystalline. Glass is not a mineral. Not because it's man-made, because glass can form in nature as well, but because it's not crystalline. The atoms in glass are arranged at random. They don't have a regularly repeating pattern. If they do, like certain types of high-temperature safety glass, it's because we've engineered them that way, and then you're back to it being man-made, and then this is how. They have definite chemical compositions. Definite chemical compositions. Which means that when you combine one silicon atom with two oxygen atoms, you will get the mineral quartz every time. Those two elements in that proportion form that mineral all the time. That's the only thing they do. One atom of zinc to one atom of sulfur is going to give you the mineral salarite every time. The combination of those two elements in that proportion, that's what results. So minerals have a definite chemical composition. There are about 90 naturally occurring elements. And they can mix and match in a wide variety of ways. Now, some elements are a lot more common than others, and some elements don't like each other. So they're not going to bond with each other anyway. So some combinations just aren't possible. But with almost 90 naturally occurring elements, we have a little more than 4,000 named, known, distinguishable minerals. And that number changes by a few every other year or so. Mostly because people discover new minerals that have not yet been described, or people discover that what was thought to be a different mineral turns out to be a variety of something we already knew about. So 4,000 minerals. In lab, you'll see and identify, I'm trying to think, 25. You're welcome. Yeah. If you take an upper level mineralogy class, I think in mineralogy we needed to know over 300 minerals. And I remember that final exam was spread out between three classrooms. And you walked into one room and it was like 20 minerals, and they were all green. So you couldn't study by, oh, that's the red one. No, you can't do that. You have to test them all. So get out of that room, you go to the next room, and they're like another 20 minerals, and they're all white. He was tough. But it was fascinating. You really learned a lot. It was really interesting. So you'll learn 25 of the most common minerals. But there are, and it varies a little bit, there are approximately 4,000 to 4,100 known minerals at any given time. Wow, that's a lot of minerals. But if we look at minerals as a whole, we're going to see in most minerals the same elements showing up over and over and over again. There's a reason for that. When studying the Earth's crust, chemists have been able to determine that the Earth's crust is most abundant in only 8 elements. approximately 98% or so of the weight of the crust. "90 elements occur in nature, only 8 of them make up the bulk of the Earth's crust. The rest, by comparison, are exceptionally rare." That's my 8. That's good. All right, and they are. Ta-da! What's the matter? Don't you know your chemical abbreviations? In the back of your book, Appendix A2 has the names and all that in the table. So I'm going to tell you what we need. Number 1 top the list. Most abundant element in the crust by weight is oxygen. Now, it's not to say that the Earth's crust is full of gas. It's not. It's oxygen that's bound, that's connected to other elements to form solid minerals. So it's in a solid state. Oxygen. Second most abundant, silicon. Silicon. Silicon is a metal. Silicon is oxygen's BFFs. They will seek each other out. They're never more than, think you get them 2 feet apart and they're like, hey! Yeah, they're always together. Number 3, Al, aluminum. Aluminum. Fe is number 4. Fe, ferrum. That's Latin for iron. Yes?
How do you spell that?
What? Ferrum. Ferrum. That's where we get Fe. Because some of the first descriptions of elements came from the Romans and Greeks. So they were first, they got the name of it. So, and early scientists, early chemists, and early scientists only spoke in Latin and Greek. In fact, if you published anything scientific, like in the 1200s, 1300s, if you didn't publish in Latin or Greek, you were considered to not know what you were talking about. Yeah. We were pretty snooty back then. Number 5, Ca. That stands for calcium. Calcium. Na. That's natrium, which is what the Greeks called sodium. So Na is sodium. Natrium was a primary ingredient to make the stuff that Egyptians used in the mummification process. K. Who's had their Kellogg's Special K cereal today? Potassium. You know, it's got K, the big red K on the box. It's not just for Kellogg's. There's a reason why they call it heart healthy, because of the potassium. It's good for your heart. It helps regulate your heart. You've got to have it. It's coming from the Greek, and I can't remember the name of the word. That's basically what the Greeks call potassium. And Mg is magnesium. Magnesium. Those are the 8 most abundant elements of the Earth's crust by weight. They make up about 98% of the entire crust. That means the remaining 2% has the other 80-some elements. If you think about what elements are absolutely positively necessary for our modern society, copper, right out there, gold, sulfur, nickel, tin, zinc, lead, silver, platinum, none of that's up there. Those other elements are exceptionally rare compared to these 8. Any questions? I don't know about you, but I'm dying. It's hot in here. Let's get the hell out of here. Go find some air conditioning.